suppose that we're being asked to find the average rate of change of this function between t equals 6 and t equals 12. In order to do this, you just basically need to find the slope of the secant line for this function between the points 6, comma f of 6 and 12, comma f of 12. So again, the average rate of change between t1 and t2 is given by the slope of the secant line joining those points. So is equal to slope of secant line. So the secant line is just essentially the line that joins those 2 points on the curve. In this case, I have that the slope of the secant line, I want to find the average rate of change between t equals 6 and t equals 12. Well, f of 6, and so let's write it out. Let's see. So one point's going to be 6, comma f of 6, and then the other point's going to be 12, comma, comma f of 12. Excuse me. Now, the slope of this line, y2 minus y1, f of 12 minus f of 6 over 12 minus 6 is just 6. And let's see what we get here. So f of 12, when I do 12, I'm going to use this bottom function g, and then they have defined values for g here. So they have f of 12. I'm going to plug in t being 12 into g, and I'm going to find out what g of 12 is. And g of 12 they give you as 474 minus 6. Again, I use the g value, the g piece for f, and they give me the value for g of 6 as 306 over 6. Now for some arithmetic, what's it going to be? If it were up to 74, to get to 374, it's 68 plus another 168 over 6. And I believe this divides evenly to 28 times. So there you go. That is your answer, 28 in this case. As for A. Part B, we may be asked to approximate the value of f prime of 9. So basically what you want to do here is you want to know that f prime of 9 is the slope of the tangent line at 9. Now, the slope of the tangent line can be approximated by secant lines. So what you do here is you find the values for t that are going to give you the shortest interval that's closest to 9. So the shortest interval is the values for t of 8 and 10. And you compute the slope of that secant line joining these 2 points. And that's going to be the best approximation for the slope of the tangent line that we can get with this information. So in order to do that, again, slope of secant line is the best approximate value of slope of the tangent line. This literally means the derivative of f at 9 is slope of tangent line at x equals 9. Now, the slope of the secant line, that's going to be equal to, again, you want to get the closest you can to 9. 9 is between the 8 and the 10. So I find the slope of the secant line joining these 2 points. This point right here, 8 comma 376, and then 10 comma 428. And I have here y2 minus y1, 428 minus 376 over 10 minus 8. And I'm going to get, this is 24 plus 28 is going to be 24 plus the 28 is going to be 52. 24. 52. Yeah, 52. So what is it? 152? No, just 52. Over 2. And then this is just 26. And this is the best approximate value I can get for f prime of 9. Determine if f is continuous on this interval, essentially where it's defined here. And the key here is that you want to look to see if the pieces of f are continuous. So right here, you have this top piece for f, and it's a polynomial. Okay, so we should know polynomials are continuous everywhere. Therefore, this top piece is continuous. Now, this bottom piece, g of t, they tell you that g of t is differentiable. It's differentiable from on its where it's defined from 6 to 12. Now, the rule is that if it's differentiable, then it's continuous. If then continuous. Now, the converse is not necessarily true. It's not that if it's continuous, then it's differentiable. That's not always true. But if it's differentiable, then you can guarantee that it's continuous. So g of t is continuous. Now, the trick is that you want to see, okay, you know this piece is continuous and you know this piece is continuous. You want to make sure that when f switches from its top piece to its bottom piece, that it doesn't break that continuity. You want to investigate what happens at t equals 6. Because if f is continuous at 6, then f is going to be continuous everywhere. Because this piece is continuous where it's defined, and then this piece is continuous where it's defined. Therefore, the only thing that you need to make sure is that these two pieces match at the same value, that there's no break. So what does that look like? Let's just get a rough sketch of f in our minds, and let's not do this in an arbitrary way. Let's understand what's happening with the graph of f. So for 0 to 6, let's say this is 6, and then let's say this is 12. I'm doing this function. Now, this function is a cubic function with a variety of properties, but I mean, at 0, it starts off as 0, and then it's going to go up to 6, I guess. It could go up, but I don't know how it goes up to 6 to this point over here, but it doesn't really matter as long as it continuously goes up. Now, the cases for how it looks at 6 are, I mean, like really two cases. It could be that it looks like this, right? And then it's continuous, right? In which case, you have it where it's discontinuous at 6 and f is not continuous on this entire interval. because it wouldn't be continuous at t equals 6. This would be a jump discontinuity. But it could look like this one. It could look like this, where it meets right there at that value and then goes up to some value. And then you see that f is continuous everywhere. And you want to essentially determine which case it's in. Now, the way to do that in an analytical way is to say, let me get rid of that piece too. Is to say you want to determine whether, again, f is continuous at 6, do limit as t goes to 6 of f of t needs to be equal to f of 6. That's the definition of f being continuous at 6. And you just need to essentially see, like, you have a value for what f of 6 is. F of 6 is going to be g of 6. And then g of 6 is 306. And then I know that after that, g is going to be continuous. So it could look like this, right? This could be 306 right here. And then I could compute the limits. I could say limit as t goes to 6. I'm investigating this now. I know f of 6 is 306. I know that if I come to 6 from this side, since g is continuous, it's going to be that limit as t goes to 6 from the right of f of t is indeed 306. Because this function, g of t, right, this is going to be the same thing as limit as t goes to 6 from the right of g of t, how they define g of t here, is continuous. Okay, so as I come to 6 over here, I'm just going to be getting closer and closer to that 306 value. The question that I need to investigate is whether or not if I come to 6 from below 6, from the left of 6, what this value is going to be. Okay, for values above 6, for values over here, I'm using this bottom piece. I'm using g of t. But for values beneath 6, right, for values above 6, I use this one. But for values beneath 6, to the left of 6, I use this one right here. And I just need to get a determination as to where this polynomial is headed. I need to get an idea of where this polynomial is headed as I get closer and closer to 6. And the way I do that is I just plug in 6 to this polynomial. And if I plug in 6 into this polynomial, what you will see is, if you take your time, let's see if I do my arithmetic correct, because I'm horrible at arithmetic, plus 6 squared minus 6 cubed over 12. Find out what this value is. Take your time with this value. But 48 times 6, 48 is 8 times 6, right? That's 48. And then times 6 again is 6 squared plus 6 squared. I don't know if this is going to make it easier or harder. Divided by, well, and then here, this will make it a little bit easier actually. This is another 6 squared. But is there a 12 in there? Yeah, there is. There's a 12 in here. So let's get rid of that 12. 12 times what is going to give me 6 cubed? Well, 6 cubed is 6 times 6 times 6. I don't know. I hate doing high arithmetic. And what is this? This is going to be 2 times 6 times 6 times 3. This is a 12. It cancels. This is going to be 18. So, let's see. This is minus 18. Yeah, minus 6 squared plus 6 squared times 8. And now what I'm going to get is a 6 squared, 8 plus 1. When I factor out the 6 squared minus 18, this is going to be 36 times 9. I don't see any way of doing this any easier. I don't know. Maybe there's easier ways. Find out what this is. You're going to get 306. Okay. And basically what you have here is that these two functions actually do meet. You have this. You have this case. This right here is your case. And this is not what it looks like it meets right here. Here's 306. Okay. And they meet. And you could say that the left-hand limit equals the right-hand limit. Limit as t goes to 6 of f of t equals f of 6. F is continuous at t equals 6. That's one thing. Then you'll have f is continuous at t equals 6, and you want to just say f is continuous on its top piece because it's a polynomial, and f is continuous on its bottom piece because it gives you that g is differentiable, and if it's differentiable then it's continuous. So f is continuous on its bottom piece, and f is continuous where it switches at 6. That's that point right there, and then you're done. Forward, if you ask me, it's asking you to find the slope of the tangent line at t equals 2, or the instantaneous rate of change at t equals 2, both same thing. Instantaneous rate of change, slope of tangent line, same thing. Derivative of f at 2, all the same thing. Here we have that when t equals 2, I'm using this top piece. So all I need to do is differentiate this top piece and plug in 2 into that. So the derivative f prime of t for t equal to from 0 to 6, not including 6, the derivative is going to be 48 plus 2t minus 1/4 t squared. Now you just want to be careful, make sure you do that right. I'm prone to making mistakes, so let's just check over. 3 over 12 is 1/4, and then it's t squared because the exponent decreases by 1. 48 plus 2 times 2, because now I'm finding f prime of 2, minus 1/4 2 squared. And this is not too difficult arithmetic. Plus 4 minus 2 squared is 4. 4 times 1/4 is 1. 48 plus 4 is 52. 52 minus 1 is 51. And then that's it.